alkene can be converted into phenol by heating in aqueous sodium hydroxide solution at a temperature of 623 Kelvin and the pressure of 300 atmosphere. Meta position is present, electron withdrawing group, it will not show any effect. But the electron withdrawing group, if it is present in the ortho and para position, it will show a reactivity. Here 2-chloroacetophenone and 4-chloroacetophenone will be formed, but 4-chloroacetophenone is the major product. Hello everyone, this is Harshita Bhavasar from Vidhyaashram PU College Temple of Excellence. Now I am going to start session 4. This is the last session of Haloalkanes and Haloarenes chapter. In the previous session, we have discussed about stereochemical aspects of haloalkanes, that is stereochemical aspects of nucleophilic substitution reaction and SN1 mechanism in optically active alkyl halides. In present session, we will discuss about elimination reactions and electrophilic substitution reactions. First, we will see elimination reaction. When a haloalkane with beta hydrogen atom is heated with alcoholic solution of potassium hydroxide, there is elimination of hydrogen atom from beta carbon and a halogen atom from the alpha carbon atom. As a result, an alkene is formed. Since beta hydrogen atom is involved in elimination, it is often called beta elimination. Means when a haloalkane with beta hydrogen, this is a beta hydrogen atom is heated with alcoholic potassium hydroxide, means KOH. Okay, there is elimination of hydrogen atom from beta carbon. This is a beta carbon, it will be removed, and a halogen atom from alpha carbon, this is a alpha carbon, and this halogen atom will be removed. As a result, the alkene will be formed. This is alkene, which is having double bond. Alkene will be formed, and that overall process which is involved in beta position, so it will call beta elimination. Once again, hydrogen present in beta position, we will call it as beta hydrogen. It will be removed from the haloalkane, and also in the alpha position which is present halogen, that halogen will be also removed, and it leads to the formation of alkene when it is treated with potassium hydroxide, and that overall process will be called it as beta elimination. If more than one beta hydrogen is present, there is a possibility of formation of more than one alkene. Such reactions takes place according to Steffitz's rule. If more than one beta hydrogen is present, then more elimination or more alkenes could be formed. So it will be takes place according to Steffitz's rule. So what is that Steffitz's rule means? Dehydrohalogenation means one hydrogen and halogen will be removed. In that reaction, the preferred product is that alkene which has greater number of alkyl groups attached to the doubly bonded carbon atoms. Means in that overall haloalkane, one halogen and hydrogen should be removed when it is treated with potassium hydroxide, that alcoholic potassium hydroxide. See here also pentene will form, but pent-2-ene, here just pentene, but here it is formed major product and this will form minor product. In this Steffitz's rule, what does it telling means? Wherever the hydrogen atoms are less in the beta position, that hydrogen will be removed. So by that it will form alkene. So there is a major and another minor product. Here the hydrogen are leastly present in beta position, so it will be considered as major product. Next, action of magnesium. This will reaction with metal. So in that action of magnesium, here when haloalkanes are reacted with magnesium, which is a metal, Grignard reagent will be formed. When an alkyl halide is treated with magnesium in dry ether medium, alkyl magnesium halide will be formed. This is haloalkane, this is magnesium in dry ether, this will called Grignard reagent. So this is Grignard reagent, it will be formed through magnesium reacted with haloalkane. Next, Wood's reaction. Alkyl halides heated with metallic sodium in dry ether medium to give alkanes. See here, haloalkane treated with sodium In the presence of dry ether, here alkanes will be formed and sodium halide will be removed. This is alkenes. Okay. And Grignard's reaction with magnesium, whichever it is forming, these are all important reaction. Next, haloarenes. The preparation of haloarenes will be seen. You know what are haloarenes, what are its classification, everything. How it will be prepared? By electrophilic substitution. Aryl chlorides and bromides can be easily prepared by electrophilic substitution of arenes with chlorine and bromine respectively in the presence of Lewis acid catalyst like iron or iron chloride. This is oral aryl and treated with halogen in the presence of iron. Orthohalotoluene will be formed and para-halotoluene will be formed. When toluene is treated with halogen, it will form halotoluene with ortho and para positions. Ortho and para isomers can be easily separated due to large difference in their melting point. How it will be differentiated? It will be differentiated through the difference in boiling or melting points. Next, Sandmeyer's reaction. When a primary aromatic amine dissolved or suspended in cold aqueous mineral acid is treated with sodium nitrite, a diazonium salt is formed. Mixing the solution of freshly prepared diazonium salt with cuprous chloride or cuprous bromide results in the replacement of the diazonium group by chlorine or bromine. This is a primary amine treated with sodium nitrite and hydrogen halide at the presence of 273 to 278 Kelvin. Here diazonium reaction takes place, benzene diazonium halide will be formed, and next treated with cuprous halide, it will form aryl halide, and that halide may be chloride or bromine will be present. Replacement of diazonium group by iodine does not require the presence of cuprous halide and is done simply by shaking the diazonium salt with potassium iodide. Chlorine bromine, it needs diazonium reaction, but here replacement of diazonium group by iodine does not require the presence of cuprous halide. Here it doesn't need cuprous halide, just by shaking it will replace the order and it will form aryl iodide plus N2. Next, reactions of haloarenes, that is nucleophilic substitution. Aryl halides are extremely less reactive towards nucleophilic substitution reactions due to following reasons. Due to certain reasons, aryl halides are less reactive to nucleophilic substitution reactions. What are those reactions? We'll see. Resonance effect. In haloarenes, carbon-chlorine bond acquires a partial double bond character due to resonance. As a result, the bond cleavages in haloarene is difficult than haloalkane, and therefore they are less reactive towards the nucleophilic substitution reaction. Here you know in the arene there is a presence of alternative double bonds, and here there is a character called resonance character, but also the haloalkane the bond breaking was little bit easier than haloarene bond breaking. So here nucleophilic substitution reaction will occur in very difficulty manner. So this is a resonance structure. See, this electron will enter here and the replacement of electrons or bonds will take place. Next, difference in hybridization of carbon atom in CX bond. First one is resonance effect. Next one is hybridization, difference in hybridization of carbon atom in CX bond. In haloarene, CX bond is less polar as carbon is sp2 hybridized. However, in haloalkane, CX bond is more polar as carbon is sp3 hybridized. As a result, CX bond is shorter in haloarene. It is difficult to break. We know that comparative version sp2 and sp3. sp3 can be easily broken comparative to sp2 because sp2 is shorter than sp3 and it is stronger than sp3. So in haloarene, that a double bond is stronger and shorter than sp3. So it cannot be broke easily. Okay. See here, this is sp2, this is sp3 carbon. And next point, next reason, instability of phenyl cation. Phenyl cation is not resonance stabilized. Phenyl means that arene, whatever the cation is present, it is completely unstable in resonance. So it is not a resonance stabilized. That is also one reason. High electron density on benzene. Because of the possible repulsion, less likely for the electron-rich nucleophile to approach electron-rich arenes. Already, the electron density is more on arene or benzene. So, nucleophile also electron-rich species. Approach of nucleophile towards the benzene, it will not more likely to get the approach from nucleophile. So, the nucleophilic substitution reaction will get less due to these reasons. Okay, these were the 4 major reasons why haloarenes will not undergo as much as possible towards the nucleophilic substitution reaction. Next, we will see replacement, the nucleophilic substitution reaction, whatever and in the what context it may form. Replacement by hydroxyl group in chlorobenzene. Chlorobenzene can be converted into phenol by heating in aqueous sodium hydroxide solution at a temperature of 623 Kelvin and the pressure of 300 atmosphere. This is chlorobenzene. By treating sodium hydroxide at 623 Kelvin and 300 atmospheric pressure, it will form phenol. This chlorine atom will be removed and hydroxyl ion will be attached. Next, in chloronitrobenzene, the presence of electron withdrawing group, that is nitrite, at ortho and para positions increases the reactivity of haloarenes towards nucleophilic reaction. Due to the nitrite ion present in the ortho and para position, the reactivity towards the substitution nucleophilic reaction may occur. However, no effect on reactivity of haloarenes is observed by the presence of electron withdrawing group at meta position. Meta position is present electron withdrawing group, it will not show any effect. But the electron withdrawing group, if it is present in the ortho and para position, it will show a reactivity. So, this is chloronitrobenzene. When treated with sodium hydroxide at 443 Kelvin, it will form dinitrophenol. Okay. If trinitro-chlorobenzene is treated with in the warm water, it will form trinitrophenol. Next, electrophilic substitution reaction. Halo group is electron withdrawing group, yet it is ortho and para directing electrophile substitution due to resonance. Halo group is electron withdrawing group, that X is electron withdrawing group, and it is ortho and para directing in electrophile substitution due to resonance. Due to minus I effect of halo group, ring gets a little deactivated. As a result, electrophilic substitution in haloarenes is slow and requires more drastic conditions. Even electrophilic substitution reactions are very slow in arenes and requires more drastic conditions to happen in that arenes. We will see first one, halogenation, which is a electrophilic substitution reaction. When chlorobenzene is heated with chlorine in the presence of anhydrous aluminum chloride, a mixture of ortho and para dichlorobenzene is obtained. This is chlorobenzene treated with chlorine in the presence of anhydrous ferrous chloride. It will form 1,4 dichlorobenzene and 1,2 dichlorobenzene. But the major is 1,4 rather than 1,2. Next, nitration. Nitration means nitrating mixture is needed, that is concentrated H2SO4 plus HNO3. When chlorobenzene is heated with a mixture of concentrated HNO3 and concentrated H2SO4, a mixture of ortho and para chloronitrobenzene is formed. Same here, reactant chlorobenzene treated with nitrating mixture, that is concentrated H2SO4 and concentrated HNO3. It will form 1-chloro-2-nitrobenzene and 1-chloro-4-nitrobenzene. But major position is 1,4-nitrobenzene. Next one, sulfonation. Here the reagent is concentrated H2SO4. Same reactant, that is chlorobenzene, when reacted with concentrated sulfuric acid, 2-chlorobenzene sulfonic acid and 4-chlorobenzene sulfonic acid will be formed. But 4-chlorobenzene sulfonic acid will be the major product. Next one, Friedel-Crafts reaction. Here the reagent is anhydrous aluminum chloride. Same chlorobenzene reacting with chloroform, that is methyl chloride. The presence of anhydrous aluminum chloride, it will form 1-chloro-2-methylbenzene and 1-chloro-4-methylbenzene, but the major product is 1-chloro-4-methylbenzene. Next, Friedel-Crafts acylation. Here also anhydrous aluminum chloride will be used, but with acetyl chloride will be reacting When a chlorobenzene is heated with acetyl chloride in the presence of anhydrous aluminium chloride catalyst, a mixture of ortho and para chloroacetophenone is formed. This is acetyl chloride and this is anhydrous aluminium chloride. Reactant is chlorobenzene itself. Here 2-chloroacetophenone and 4-chloroacetophenone will be formed, but 4-chloroacetophenone is the major product. Next, reaction with metals, that is Wurtz-Fittig reaction. When a mixture of alkyl halide and aryl halide is heated with sodium in dry ether medium, alkyl benzene is formed. We know sodium is a soft metal. Here, the mixture of alkyl halide and aryl halide is treated with sodium. This is aryl halide, this is alkyl halide. Treating with sodium, which is a soft metal, in a dry ether condition, it will form aryl and this is sodium halide. Okay. If we take bromobenzene as a example with sodium, this is bromomethane, and here dry ether toluene will be formed with sodium bromide. Next, only Fittig reaction. When aryl halides are heated with sodium in dry ether, two aryl groups join together forming biphenyl. When aryl halide treating with sodium in the presence of dry ether, biphenyl will be formed. Two aryl ring attached here. So, biphenyl with sodium halide. Next, polyhalogen compounds. Already we have seen the preparation of haloarenes and the reactions of haloarenes. Now we will see polyhalogen compounds one by one, its uses and its environment. First one, dichloromethane, CH2Cl2. How it will be used? It is used as solvent in drug industry, paint remover and propellant in aerosols, a cleaning reagent for metals, medium and alkyl benzene is formed. It is a solvent in medicine industry or drug industries, and it is a paint remover and it's a clean agent for metals. What is the environmental impact? Its direct contact to our skin develops redness and burning sensation. It is harmful to our central nervous system. Its high level in air causes nausea, numbness in finger and toes. It is not that much good to our environment. It may cause skin irritation, skin redness and also nausea, numbness in fingers and toes. But it is having some of the applications. Next, trichloromethane, that is chloroform, CHCl3. Chloroform is a sweet smelling liquid, boiling point having 334 Kelvin, non-inflammable, but it is vapor causes unconsciousness. Chloroform is a sweet smelling or sweet odoring liquid. It is having the boiling point of 334 Kelvin and it is inflammable, means it will not catch fire, but that vapor causes the unconsciousness to a person. When exposed to sunlight and air, it slowly decomposes into phosgene, a poisonous gas. It is therefore stored in closed dark colored bottle, completely filled so that air is kept out. When it is exposed to sunlight, it will form the compound called phosgene and it is a poisonous gas. So, it will be covered completely in a dark bottle which should not expose it to sunlight. When treated with oxygen or a light, phosgene, COCl2 will form with the liberation of HCl. What are the uses? As a solvent for fats, oils, varnishes, waxes, resins and rubber, etc. Though it is having a disadvantage, but it is also act as a solvent for fats, oils, varnishes, waxes, resins, etc. For the preparation of chloroetone, it is a drug, and chloropsyrin, it is an insecticide. As an anesthetic after being mixed with ether. After mixing with ether, it will act as anesthetic in the manufacture of freon, that is a refrigerant. In the manufacture of freons also, which is a refrigerant, it will be used. What is environmental impact? On inhalation, it depresses the central nervous system and causes the headache and dizziness. Chronic exposure damages liver and kidneys. On exposure to sunlight and air, it slowly decomposes into phosgene. Ethanol 1% is added to retard the oxidation of phosgene into harmless ethyl carbonate. Okay, these are the 4 environmental impact. Already we have seen it causes headache and dizziness and it will form phosgene, which is a highly poisonous gas. Next, triiodomethane, that is CH3 iodoform. It is a yellow crystalline solid, pungent characteristic odor, melting point is 392 Kelvin and it is steam volatile. It is used as antiseptic for dressing wounds. It is a yellow colored crystalline solid having pungent characteristic, and it will be used in dressing wounds. It is a steam volatile. Uses as antiseptic for dressing of wound in the manufacture of certain pharmaceuticals also. What is the environmental impact? When it comes in contact with skin, iodine is liberated, which is responsible for antiseptic properties. It has an objectionable smell, and it is a pungent odor, and it will be antiseptic when it is treated with skin. Next, tetrachloromethane, that is CCl4, carbon tetrachloride. It is a liquid boiling point of 350 Kelvin, non-flammable, hence used as a solvent for fats, oils, waxes and resins, etc. It is used as fire extinguishers under the same name, pyrene. Usually CCl4 will be used as fire extinguishers, and due to its non-flammable character, it will be used as solvent for waxes and resins. Uses: it is used as a fire extinguishers, as a solvent and also dry cleaning. In medicine, helminthicide for elimination of hookworm. Environmental impact: its vapor when breathed cause nausea, dizziness, vomiting and may cause damage nerve cell permanently. On exposure, it causes cancer, irregular heartbeat and person may go to coma also. Its vapor depletes ozone layer. Ozone hole permits the ultraviolet radiation to the reach earth and may cause skin cancer, eye disease and disorder. It may adversely affect our immune system. Okay, these are the environmental impact. Usually all these solvents will cause the dizziness or nausea, headache, skin irritations like skin cancer, anything it may cause. The major CCl4 may depletes the ozone layer also. Next, freons, that is chlorofluorocarbons. Freons are small organic molecules containing carbon, chlorine and fluorine. The most common freons are CF2Cl, Freon 12 and CF3Cl, Freon 11. What are the uses? In air conditioning and domestic refrigerators for cooling purposes. These CFCs or freons will be used in air conditioning or refrigerators for the deep freezing or cooling pressure. As propellants in aerosol and foams to spray out deodorants, cleansers and insecticides, halothane is used as inhalation anesthetic. And environmental impact: most freon eventually makes its way into the atmosphere where it diffuses unchanged into the stratosphere. In stratosphere, freon is able to initiate radical chain reaction that can upset the natural ozone layer surrounding the earth. These freons or CFCs will also started depleting the ozone layer, which will protect from UV radiation to the earth. Those about ozone layer depletion we know from our previous classes also. Next, dichloro-diphenyl trichloroethane, that is DDT, uses as an effective insecticide for mosquitoes, flies and crop pests, as an anti-malarial. Environmental impact: DDT is the first chlorinated organic insecticide. Its stability and fat solubility is a greater problem. It is prepared from chloral and chlorobenzene in the presence of concentrated H2SO4. Dichloro and diphenyl ethane. Okay, this is the structure, and it is effective insecticide from the ants, flies, also mosquitoes, and it is anti-malarial, which is a very poisonous also. Okay, this is the structure of DDT. And this completes the chapter Haloalkanes and Haloarenes. I hope you have completely understood the introduction part of haloalkanes and haloarenes, its classification, its preparation and its stereochemical aspects and various kinds of reactivity of haloalkanes and haloarenes. And this is about polyhalogen compounds. And I hope you have completely gone through the previous classes. You have understood very well. So we'll meet in the upcoming next new chapter. Till that, thank you.